I'm Ryan Baker, and this is Big Day in Education. Today we're going to continue our discussion of knowledge inference by talking about performance factors analysis, a popular competitor to Bayesian knowledge tracing. PFA addresses some of the limitations of BKT, but it doesn't quite have all of its nice features. There's a real trade-off to be made. It was proposed in 2009 by Pavlik, Sen, and Katinger. PFA measures how much latent skill a student has while they're learning, but it expresses it solely in terms of probability of correctness the next time the skill is encountered. There's no direct expression of the amount of latent skill in PFA, except this probability of correctness. In PFA, you assess a student's knowledge of topic or skill X, knowledge component X, based on a sequence of items that are dichotomously scored. Or in other words, the student can get a score of 0 or 1 on each item. And the student can learn on each item due to help, feedback, or scaffolding. How does PFA differ from BKT? Well, let's talk about its key assumptions. First of all, each item may involve multiple latent skills or knowledge components. This is a big difference from BKT. In BKT, it's the assumption that there's only one skill per item, and that means that you can only really use BKT in situations where you've designed the curriculum so there's really only kind of one relevant skill, one skill with a chance of being hard at any given time. PFA doesn't make this assumption, and so it can be used a little more widely. Also in PFA, each skill has a success learning rate, gamma, and a failure learning rate, rho. And that's different from BKT, where the learning rate's the same, success or failure. In fact, these success and failure learning rates take into account not just learning, but also they take into account what it means that you've failed or succeeded. So they take into account that you failed or succeeded, as well as the learning based on those cases. PFA also has a difficulty parameter beta, but its semantics can vary. More on this later. From these parameters, and the number of successes and failures the student has had on each relevant skill so far, we can compute the probability, P of m, that the learner will get this item correct. So PFA can be expressed mathematically as follows. First you compute m. M is a function of beta, the difficulty, and the sum of the number of successes and failures with their weight parameters, gamma and rho, that students have had on every relevant skill in the problem. You take that m and then you put it through an exponential function. So let's look at an example. We'll start first with a reasonable example. We'll move on to crazy examples later. Let's say that you have gamma of 0.2, rho of 0.1. So we're assuming that you improve your future performance double if you get success compared to if you get a failure. And beta is negative 0.5, which means the item's a little hard. So the initial m, there's no successes or failures yet, is going to be negative 0.5. That's the beta. So the probability the student will get it right on the first attempt is 0.38. At this point, we have no information about the student. It's like L0 in BKT. And in fact, let's say the student gets it wrong. Now we update for the next opportunity m. We take that negative 0.5, item difficulty is the same here. We haven't really talked about this yet. And we add, for that failure, 0.1, the rho, times 1 failure so far. And this gives us negative 0.5 plus 0.1, which gives us negative 0.4. So we say the probability they'll get it right is 0.4. Even though they got it wrong, we're saying they still learned more than the evidence of them being wrong told us they won't get it. And in fact, let's say the actual 0. In this case now, the m will be negative 0.5 plus 0.1 times 2. We've got 2 failures now that are weighted 0.1 for rho. Negative 0.3 is the result, which gives us a p of m of 0.43, and the actual is 1, let's say. So now they have 2 failures and 1 success. So now the function's just a little more complex. It's negative 0.5, the beta, plus 2 failures, 1 success, which gives us a probability of m of 0.48. And you can see it's kind of just going up over time. Now let's look at a degenerate example. Let's say that instead of having a gamma of 0.2 and a rho of 0.1, we have a gamma of 0.1 and a rho of 0.2. In other words, you're twice as likely to do better in the future if you get it wrong than if you get it right. So what does this really mean? This means that if you fail, it's more likely to be associated with future success than if you succeed. And I think sometimes this is how we fund startups, but that's a different story for a different class. Now let's think of the case of negative learning. Let's say we actually have a rho of negative 0.5. In this case, they have a m of negative 0.5 and a p of 0.38. They get it wrong. Now their m is negative 1, which is associated with p of m of 0.27. Then they get it wrong again, negative 1.5, p of m of 0.18. Finally, they get it right. It starts to come up again. Now, this looks weird at first. It's certainly not something you have in BKT. There's not negative learning in BKT. But It's actually not crazy, because think about it. In this paradigm, values of rho below 1 don't actually mean negative learning. They mean that the failure provides more evidence on the student's lack of knowledge than the learning opportunity causes improvement. So it's got a totally different semantic. It's not really negative learning. It's just you gain more information that they don't know it, then the learning opportunity exists. So parameters in PFA combine information from correctness with improvement from practice improvement. And this makes PFA models a little harder to interpret than BKT. Nothing wrong with it, just you have to think a little more deeply. So how about adjusting beta? Let's say if you adjust beta. If you look at this case, we got that beta of negative 0.5. You saw this pattern before. If we change it to negative 1.5, the same kind of amount of improvement happens, but they start from a lower baseline. And if we set beta to plus 3, then it starts with a really high baseline. From the very start, we assume a student's going to be 95.3% correct. Incidentally, if we think a student's going to be 95.3% correct, it probably is relatively unlikely that you want to give the student this item to study unless there's some really good other pedagogical reason. For example, to help them kind of solidify their knowledge, although that's an issue for attention, for memory strength. That's something we'll talk about later in the week. That's not a case where you really want to use PFA or BKT. Or maybe it's just a step that you kind of have to do in getting to another step, and it's just too much of a pain to design something that skips it. For example, entering a given in a worksheet. It may not be worth actually letting the student skip that step. So for beta parameters, Pavlik proposes 3 different beta parameters: item, item type, and skill. And so is the difficulty something that each item has a difficulty? Is the difficulty something that each skill has a difficulty? Or are there kind of types of items somewhere in between? These 3 approaches result in different numbers of parameters and greater or lesser potential concern about overfitting. The more parameters, the more risk of overfitting. So how do we fit PFA? Unlike BKT, where there's several alternatives that people consider, typically for PFA, just expectation maximization is used. It's pretty simple. First, we start with initial values for each parameter, which are typically arbitrary. We then estimate student correctness at each problem step or item based on those values. We then re-estimate the parameters using the student correctness estimate. And if the goodness of the model is substantially better than the last time it was estimated, and we haven't reached some pre-chosen threshold for the maximum number of iterations we can do, we go back to step 2. We re-estimate student correctness from the parameters, we re-estimate params from the student correctness, go back to step 2, and keep going until you kind of don't get any better, or you get to a point where you've gone through your maximum number of tries. Now, EM is vulnerable to local minima, which means that sometimes you get to a parameter space where there's actually a much better one over somewhere else, but you can't get to it from where you are. And to try to avoid that, randomized restart is typically used. So is PFA better than BKT? Actually, it turns out that they have approximately equal predictive power across a lot of studies, all done, as you can see, about 7 years ago. There's different virtues and flaws for the 2 algorithms, so choose the one that better fits your goals. So some final thoughts. PFA is a competitor for measuring student skill, which predicts the probability of correctness rather than latent knowledge. But it has a big virtue: it can handle multiple KCs for the same item. So next up, item response theory, which is a classical method even older than BKT, which solves a different problem. So I'm Ryan Baker. This is Big Data in Education. Thank you very much. See you next time.